Okay, so we're on to problem 55. So 55 has a slope of 0. So, and it goes through the point 2, -5. So slope of 0 is this. That's m equals 0. If you have a vertical line, m is undefined. So because this is a horizontal line, slope m equals 0 means horizontal. What that means is that the value of y is the same for the entire plot. So all you have to do is go over here and find the corresponding y value. So it's y equals -5 is the equation. And so if you take graph paper, if we locate the point 2, -5, so we go 2, -5, 1, 2, 3, 4, 5. So that's our point. So a horizontal line is going to go through that point, and it's going to have, no matter what the value of x is, the y value is constant. So that's y equals -5, which does go through the point 2, -5, -2. Or was that 2 or negative? Oh, I did that wrong. It's actually supposed to be over here, 2, -5. But -2, -5 also goes through at any point that has the second value. The y coordinate is -5 is on that line. So you can say y is independent of x, meaning that it doesn't matter what the value of x is, you have the same value of y. Okay, then we have 58, which has an undefined slope. So we said undefined slope means vertical line. And so if we get a graph paper again, and we plot the point, which was -3, 1. So we go -3, 1. That's there. So if you have what vertical line goes through this point, well, there's only one vertical line that goes through the point. So let's go like that. So what we can say here is that the x value is independent of y. Any y value will give you an x equal to, did I do that wrong again? I did, didn't I? Why am I doing that? So it's -3, 1, -1, 2, 3, 1. So that first one's a mistake. Okay, so that's the drawing. Now, the next two are just word problems, and the reality is that, you know, most physical phenomenon, whether you look at it experimentally or whether you look at it theoretically, most of the time the relationship between variables is linear. And that can have a positive slope or a negative slope. But even though linear seems, well, I've been doing that since 8th grade or 9th grade, the actual applicability of linear things to real world problems is fairly well true. So, okay. So we're going to do problem 61. Actually, that's not, I was sorry about that. Still got one more to do. So it says, determine whether the lines described are parallel, perpendicular, neither parallel or perpendicular. So what we have in this case is we have two lines that are defined by two separate sets of points. So 61 is, it says line 1, L1, goes through points 2, 0, and 5, 4. And line 2 goes between 6, 1 and point 2, 4. Now, So what we're doing is we want to know whether it's perpendicular, that's what we use as symbol for perpendicular, parallel, or neither. So we could say neither parallel or perpendicular. So those are the three choices. Now, parallel lines, basically the thing here is parallel lines have the same slope value. So that's how you tell whether they're parallel. Perpendicular lines have slopes which are negative reciprocals. And if they're neither one of those, then they are neither parallel nor perpendicular. So to answer this question, we basically need to calculate the slope of these 2 points for this line associated with these 2 points. I'm going to go ahead and call one x1, y1, call one x2, y2, and I'm going to do the same thing down here, and we just have to make sure we don't mix these up. So we're going to do these, and then we're going to do this separately. So remember, slope is y2 minus y1 divided by x2 minus x1. So for line number 1, y2 is 4, y1 is 0, x2 is 5, x1 is 2. So we get 4 divided by 3, 4/3. Now the negative reciprocal of this number the negative reciprocal of 4/3 is, so we put a negative sign out in front of it, and we take the reciprocal of the fraction. Reciprocal means it's 1 over number. So, you know, if A is a number, then the reciprocal is 1 over A. So that's the relationship between a number and its reciprocal. One is 1 over the other. Okay, now, for you guys who've taken first semester, you know that when you divide by a fraction, it's the same as multiplying. So we got the numerator, we got 1. You multiply by the reciprocal. So instead of 1 divided by this, it's 1 multiplied by the reciprocal. So we'll get negative 1 times 3, which is negative 3, divided by 4. So that is the negative reciprocal of 4/3. And really all you have to do is, when you have a fraction or rational number like this, is you just flip these two. So 4/3 becomes 3/4, and you put a negative sign in front of it. So if line 2 has the same slope as this, then they're parallel. If line 2 has this slope, then they're perpendicular. And if it has neither one of them, then it's neither. So again, now we need to go ahead and calculate the slope of line 2 and see how it compares with parallel, perpendicular. So we come over here, y2 is 4, y1 is 1, x2 is 2, x1 is 6. So I get 4 minus 1 is 3, 2 minus 6 is negative 4. Okay, so that's what I'm comparing. So notice these are the same. And so what we can say is, since M2 is the negative reciprocal of M1, the two lines are perpendicular. So that was 61. And I'll do another one in class which is parallel, so you should have seen that already. See the other example. Okay, and then we got these word problems. There are not too many of them. So we're just looking at 70, I think. 70, yep. So it says personal spending on recreation in the United States in billions of dollars in recent years is closely approximated by this graph. So what you see is a graph that has an x-axis of years, a y-axis of spending in billions of dollars. So in 2000, you see there's a point, year 2000, $268.3 billion. In 2006, you see a point, 2006, comma, 381. And then you see a straight line drawn between those two. So what they're asking for is the average rate of change. So rate of change is basically the change in something per unit time. So in our case, our unit time is a year. So we want dollars per billion dollars per unit time. So the way you do that, the rate of change is basically the slope of the something versus time. So the x-axis, which is the run, is going to be time, which is the denominator. So it all makes sense. So all you have to do is to find this rate of change is basically find the slope of the line. If you find the slope of the line, if you plot time on this axis and something over on this axis, and you can get 2 points like that. The slope of the line connecting these two is going to be the rate of change. So all we have to do in our case is we have to look at how much the spending changes, and I'm just going to do it in millions. I'm not going to write all billions. I'm just going to write out 381 instead of 381 billion. You subtract the total change over, in this case, 6 years. So that's the total change in 6 years divided by the number of years. Well, the number of years is the difference between the two calendar years. 2006 minus 2000, that's 6. And so then we just plug those into our calculator. And what we end up with is, well, one other thing is we would want to write down what the units are. I'm just using numbers. But rate of change is important to have the units. So this would be billions of dollars. The denominator would be years. So when you do that, you'll get 381 minus 268.3 divided by 6, and I get 18. I'll round it off to 3 digits. 18.8 billion dollars. I'll write it out. $1 billion per year. So each year, on average, the spending is increased by $18.8 billion over 6 years. If you multiply this times 6 and add it to 268.3, you're going to get 381. And so we didn't have the intermediate data, and it's probably not going to fit exactly to this curve. We plot the individual data points, it's probably going to be something like that. But the average rate of change is the difference between the beginning and the end, and we're not so worried about what's happening in the middle.